Okay, hey guys. Um, I'm making you a video to explain to you, I guess, the structural analysis of the boat. So let's start. Um, I'm a little distracted. Okay, so let's start by the loading conditions. Premise of the boat, a beam. So the boat's actually like this. We have a couple different loading cases. We have 2 paddlers or 4 paddlers, and all these loading cases include self-weight, poorly drawn. You get my idea. Okay, so the first thing I think about is how we're going to model our restraints. So let's go back to it just being a beam. So we start by looking at the restraints. A lot of teams, what they just do is they put like a pin here and a roller here, and they calculate the bending moment in the shear force diagrams. Now, I guess that's a good start, but this, to me, really does not model the behavior of the water on the boat, since the water supports the boat the entire length. It doesn't just support the tips. So, what some teams do, and I tried to do last year, but I found some flaws in it, is to model it as a uniformly distributed load along the entire bottom of the boat. That's already better, right? So the water is supporting everything equally, and then you have your boat, your 4 paddlers here. Now, if we look at the summation of forces in y, this you can make it equal to 0, right? So take these and divide it by the length, and it'll equal this force. But now, what you do is you look at the summation of moments at any point. Will this actually be equal to 0? And that's not going to work out. Because if we can look at this, pretend it is, okay? So we take summation of moments about here. For some reason, it works out. Let's say this paddler moved here. Now, the moments would change, but the boat's not going to start spinning in the water. Or this is not going to work. Or if this guy moves over here somewhere, something has to change in the reaction force to account for that movement of the person. I don't know if that's very clear, but think about it. Or just do it by hand, you'll figure it out. Okay, so what we actually have to model is that the boat, the buoyancy force, is a function of the volume displaced in the boat. So actually it looks kind of like the boat itself, buoyancy force. Well, the submerged section of the boat. That's an arrow, and that's an arrow, and that's an arrow. That's an arrow, and that's an arrow. That's an arrow, that's an arrow. You get my point. We have 4 people here. And summation of forces in y will equal to 0. And summation of moments about any point will equal to 0. So let's do the same thing I kind of did before. Say I think summation of moments about this point is 0, and this is the equilibrium condition. Let's say this guy moves it to the boat. I'm sure you guys have been in boats before, hopefully. Well, what's going to happen to the front end? It's going to go down. So the volume submerged here is going to increase. So this will get bigger around here because the front end is going to come down. These rows get bigger, and we'll retain our summation of moments in 0. So that's what we're going to try to figure out. So now the hard part is figuring out what these forces are for the different loading conditions. Lucky for you guys to figure that out. So what I did last year is I created a program that has 20 point loads on the bottom of the boat. And these point loads, okay, I'm not going to draw 20, I'm going to draw how many there are. Each of these point loads are a function of the volume submerged in the boat. So this point load is a function of the volume of the boat for like this kind of front end here, and this point load is a function for this volume, this is a function for this volume, this is a function for this volume. Now, what it does is it runs a loop. Pretty much the first step in the loop, well, we'll have our loading condition, so there's a couple, I'll go through the code after, there's a couple loading cases. Let's take 4 people. So there's 2 steps in the main loop, where first it's going to try to satisfy the summation of force in y equal to 0, and then it's going to try to satisfy summation of moments about a point, I think the point is here, equal to 0. So, first step, apply the loads, and the boat, if you want to visualize it, when you start, this will be the boat. The first step in the iteration, and it's not in the water yet, so water level is there. What it's going to do, the code is going to slowly drop the boat in the water. It's the worst drawing ever. It's going to calculate these arrows for each step until it satisfies summation of forces y equal to 0. Don't forget we have the self weight here too, but for clarity I won't try it. So now it's in a condition where this is satisfied, but maybe not the summation moments about 0. So then it'll calculate it, and it'll find out that either the boat has to come more down this way or more out this way to satisfy summation moments at 0. So right now the boat's level in the water, level in the water, and summation of forces in y are 0. And for example, maybe we have extra moment this way. Well, what the boat's going to do is it's going to try to create a counter force for that. So the program is going to do is going to start tipping the boat. I think it tips off the tip here. So it'll drop the boat, but instead of vertically down, it'll drop this volume more than this volume. So it'll weight, I guess, these buoyancy vectors more until summation of moments about 0 is solved. So I think the program's called like pitching angle or something like that, because it pitches the boat up and down in the water to try to figure out where it rests. Because at the end of the day, the boat doesn't stay horizontal in the water. It kind of takes an angle to solve for the moment conditions. So now we have this summation of moments equal to 0 solved, but by pitching the boat, we've lost this equilibrium condition. So then it calculates it, and then it figures out if the boat has to go up or down, and it raises it. So let's say, because I dropped it, I'm increasing the buoyancy, so now the boat wants to come up. So then it'll take this slanted section of the boat, and it'll bring it up until here maybe, until summation of forces in y equal to 0 is going to satisfy. But then summation of moments about 0 is not satisfied anymore, and it calculates which to go. And then maybe it'll spin the boat this way a bit, and then the boat will be like this kind of. And it keeps repeating this process until a tolerance is reached, and eventually you can see that it'll kind of hopefully converge on the resting position of the boat. So that's, I guess, the basic principle of the code. Now I haven't looked at this thing in a long time, so let me find it first. Pitching angle. It's this one. Let's open that. Okay. So this is important. So this is an Excel. It's an Excel file with the boat profiles, 20 different boat profiles for an eclipse. So Harry or Thomas, or actually anybody can do it, whoever volunteers. So I thought I had coded it directly into MATLAB, but I didn't apparently. I'm gonna have to go and take the new boat shape, export 20 stations, and create these vectors. So these vectors are the boat profiles at 20 different spots on the boat. Then I have a loop that I guess separates the profiles so I can use them. Here's some comments. So here's my assumptions for the loading. So self-weight of the canoe was 0.6867 kilonewtons. This was a girl, this was a guy. You guys can look in Ship with the weight it gives you and correct this value, then change it over here somewhere. And then I got different loading cases. So first loading case was self-weight only, 2 female paddlers, 2 male paddlers, and 2 male paddlers, and 2 female paddlers. So here are the loads. And this is where I was playing with it. I had a meeting because they were complaining with me. Experiments our boat sank last year, as you guys know. And that's because of the extra weight of the boat. And my program said the boat was going to be fine because I didn't account for the extra thickness, because that wasn't what we designed for. And then I wanted to see if my program was valid. So if I put the extra weight on the boat, would it sink? And it did sink. So I kind of like proof checked myself, I guess. So, but for this, I'll put back the old weight here. Oh. So, this is just a switch statement which calculates the moment on the tip of the boat, I think, and I'm not sure what this is. This is definitely a moment equation here. And this is a weight. This is a total weight, and this is, I guess, the moment on the tip from the applied loading. If we want to be really fancy, we can try to make the self-weight a function of the stations, but I don't think we need that much of a difference. Okay, so here is the fancy schmancy stuff I wrote, I think. Oh my god, I don't remember myself. This is the raising and lowering of the boat loop. And this is the checking which way we have to go. It's commented. Maybe I should have read this before talking to you guys. But you guys can read it to me if any questions. You just ask me, because I did put some comments in here so you guys can kind of figure it out. Yeah, so this has to, everything it has to do is just raising and lowering the boat, pretty much determining which way we have to go up and down with the boat, and then lowering it or raising it until that condition is satisfied. And then the second loop here pitches the boat at an angle until that's satisfied. And this is all inclusive in a gigantic loop, I think, here. Yeah, so I had 3 iterations on that and I was able to solve. And then at the end, I have just some plots. I think I used to check stuff, and some shear force diagrams that it creates, and a bending moment diagram, I believe, over here, yeah. So let's run it. Hopefully it still works after after 1 year. Change folder. Run. Let's wait a bit. Okay, enter case number. So let's go with the worst case number, which is case number 4, which is 4 paddlers. Okay, yeah, so this is going to show you, that's the buoyancy force. It's going to try to convert. This program takes, I think, about 2 or 3 minutes to solve, or maybe not. Yeah, so there's a lot of plots, and we'll just let the program finish, and then we'll talk about them. What's happening here? Oh, because I ran it twice. I'm dumb. Okay, let's just run it again. See, that was the rate. That was the first thing you saw, was the boat getting lowered and the volume increasing, and then it pitched it, and then it raised it, and then it pitched it, then raised it, and it pitched it. But the second and third iterations are a lot smaller because they're a lot closer to your final answer. So we have a whole bunch of plots here. The first 20 plots are actually the different stations the boat submerged. So this is how much the boat's sitting in the water. So the front end is barely in the water. Well, the front end is not very big on that eclipse, but these are different ends. Here we go. And I'll run it after, but you'll see if I run the case 2 or 1, which is the self weight, the boat is a lot less submerged. Then after here, this is our shear force diagram. Technically, this is where the paddlers are sitting. But that's something you guys can change, play around with. I had the paddlers at a fixed spot based on what we chose. You guys can move that around, maybe, on the boat. And technically, it should be straight up shots from, like, if you remember statics, a point load is straight. But since we do like 20 different segments, you kind of get this plotting. Like, I have a data point here and a data point here, so instead of putting it straight up like this, it puts these angles. But for the report, we can take these values and make a nicer graph. And then I have a bending moment diagram here. Maybe I should have made axes and stuff, but this is the length of the boat in feet, and this is bending moment in kilonewton meters. So you can see the boat is fully supported, so there's not a lot of bending moment that develops in the boat. So this is negative 1.2 kilonewton meters, which is like nothing. It's like well, it's significant for, I guess, boats maybe, but like on a building, that's a joke, like literally. So that's the program. I'm going to show you, I guess, with case 1. show you the difference on how the boat sits in the water. Yeah, the first part takes long because there's a lot of data to intake from Excel, and that always takes long in a math lab. So case number 1. I think some of the cases took longer to solve, but not anymore. So you can see the boat, just the self-weight, it's hardly in the water. And the shear force diagram is a lot smoother because I have no point loads, it's just the self-weight. So here we go, look at it. See it there. It's kind of in the water, like in the midpoint, it's about, it's not too deep, it's not bad. And, you know, shear force diagram, and bending moment diagram. The bending moment diagram, something we have to fix here at the end. This all is okay. There's a problem with like the last number or something. This should be 0, but it's not. But we'll have to fix that because we have to actually give calculations this year. Last year we didn't. But we'll look at that. So you guys can take a look at the code. You have to go play around with it. Input different values, and we'll talk about it. I don't know. You guys get your way. Like I said, we can make the boat sink, I guess, if you want. I think this was 1.2 before. And so I think that's what I calculated if it was and with the extra thickness and the 4 people in the boat. Also here I factored the loads. I think we don't have to do that because, I mean, we know how much the paddlers weigh, and I don't see why we have to factor them because we're sure of their weights. We know how much the paddlers weigh. Factoring is for uncertainty, and even the dead load. Maybe the dead load will be factored because we're not sure exactly how much the boats can weigh in the end. But the live loads, I don't see a reason why we should factor them. So this one takes a lot longer because pretty much what happened is the boat sank, so we're over the total volume and it can't find a solution. So it's just going to run through the iterations and it's going to just give you crappy, shitty graphs. I don't know how long this is going to take though. Yeah, you can just skip forward this part. I have actually zero idea how long it's going to take. Okay, well, this is still running. I don't know what I can talk to you guys about. I mean, I could try to explain this, but I mean, I wrote this a long time ago. And the logic's there, so don't play with it and you should be fine. If you have to change locations, you have to change a couple numbers in here, so maybe one guy wants to go through and kind of figure out what it really does. Make sure. Yeah. This is probably what I would spend the most time working on last year, was this code. Hollow spreadsheet didn't take that much time in comparison to this one. It had a lot of bugs, and I was kind of developing as I went, trying to solve the statics, and I couldn't do it, and then I figured out why it made sense, and yeah, it took a good amount of time. Okay, screw this thing, it's not plotting. I forget about that. But yeah, you guys get the idea. If you want to wait for it to finish, you can watch it. You'll see that the plots will be over the whole submerged profile of the boat. And yeah, so that's it. I think this is in Google Drive, but I'll check after this video and just make sure it is. So yeah, enjoy.